The third talk for today is by our third speaker is Shankar. He is a physical oceanographer and he's chief scientist at the CSI National Institute for Oceanography at Goa. He also has a Chennai connect. He did his undergrad in our neighborhood here at IITM, and his undergrad was in aeronautical engineering. But his subsequent research, he has come down to the marine sciences. He works on projects that provide basic data on ocean currents. He develops models to study, to understand the dynamics of the waters of the North Indian Ocean. He received the Shanti Swarup Bhatnagar Award for Earth Sciences. This was 12, 13 years ago. He is a fellow of the Indian Academy of Sciences and the National Academy of Sciences. He's going to tell us today, to share his insights about how our understanding has evolved, our understanding of this peninsular region that we live in, surrounded by the waters of the Indian Ocean, the dynamics of these waters. Our understanding has evolved over the years, and he will tell us more about it.
So thank you, Matt Science, for this invitation. It's very unusual to be speaking in front of this heterogeneous an audience, so it's a first-time experience for me. Dynamics is the response to an applied force, and the object in this case is the North Indian Ocean, the seas around India. The applied force is coming from the wind. So how do we study the oceans, and how has our understanding of the dynamics evolved over the last few decades, and maybe a peek into the future, what lies ahead? That's what this talk is about. It's broken into 4 parts. We'll see that as we go along. But one thing to remember is please don't bother to read the slides. That's more meant for me, because I'm not even sure a font is good enough to be read at the back. And it's more like following a football match. You don't have to remember every slide. The details are not important. So just stay with me as we go along, and maybe at the end, I hope there'll be a result. So what's the observed circulation like? I mean, before we start explaining what we are seeing, what exactly do we see in the oceans? So this picture that you see here is very similar to what Pi picked out in that movie Life of Pi, when he woke up the morning after he was cast adrift. And he was cast adrift somewhere here near the Philippines. And over 200 days later, having drifted in the Kuroshio, that's the western boundary current of the North Pacific, and the North Pacific current right across the basin to the eastern boundary, he was picked up somewhere off the Mexican coast. At that time, he was traversing the California current. This is called a gyre, a closed circulation. And it's closed by the north equatorial current, which flows towards the west. So you have the Kuroshio, that's the intense western boundary current. You have actually a drift right across the basin towards the equator. Poleward means towards the pole, that's the direction of all these western boundary currents. And you have the conservation of mass, so you have an equatorial drift over the rest of the basin. Now this pattern repeats in the South Pacific, in the North and South Atlantic, and the South Indian Ocean. So there must be a common explanation for what we are seeing. We study this using what's called fluid dynamics. Dynamics we understand, that's Newton's laws. The rate of change of momentum is equal to the applied force. We apply that to a fluid, and there is one dramatic change that takes place. We are no longer tracking an object. For example, if I throw this as a projectile, you track it in space as it moves. That's solid body dynamics. In a fluid, we don't do that. We actually make measurements at different locations over time. And that is how we want our answer. So we basically have what's called a field, like a magnetic field or an electric field. So that's fluid dynamics. But there's a very big difference between the flows in the ocean or the atmosphere as compared to what you see in an IC engine or even past a big ship. The biggest ship is about 450 meters. So it's very small compared to the kind of scales we are talking about. The Pacific is 20,000 kilometers across at the equator, from Papua New Guinea to Peru. The depth is just about 5 kilometers on average. So if I were to look at the ocean as a tank of depth d and length l, the ratio of d by l is very small. If the length is the length of this line here, the thickness is drawn to scale. That's the thickness of the ocean. So you don't find these kind of flows in classical engineering fluid flows. So that's one major difference. We are looking at very thin fluids. If you're looking at the entire expanse of the Pacific, about 20,000 kilometers, half the globe, you can no longer ignore the sphericity of the Earth. So we have to take into account the fact that we are no longer on a plane. The Earth is a sphere, and worse, the sphere rotates. It spins on its axis, and we are sitting on that sphere and making all our measurements with respect to that sphere. So you get, as you get on a merry-go-round, the centrifugal force, here you get a very important pseudo force called the Coriolis force. It changes everything. You can go through an entire course on mechanical engineering or aerospace engineering without encountering waves, except shock waves in supersonic flows. But in geophysical fluid flows, from the word go, you see waves. Oscillations dominate everything. And they are at a variety of scales. You have wind waves and swells at what you see when you just go out to sea. You go to the beach, Marina Beach, and you will see the waves coming in. They are at very short length scales and time scales. At the other end, you have what's called the global thermohaline circulation, which runs over decades to centuries and covers the entire planet. So this Coriolis force, it dominates the flows that is of interest to us, because we are talking of the dynamics of the North Indian Ocean. So we are talking of large scales, and we are talking of what happens, say, over a season. So it's much longer than a day. So the spin of the Earth has an impact. What does it do? Now there are two cases we look at. One is when you have the wind blowing on the surface of the ocean. So suppose this is the ocean here. We fill this entire hall, flatten it out and fill it with water. And I pull a sheet, a stiff sheet on top of it from me towards you. If it is a classical fluid flow, the water would just move with the sheet towards you, and the motion would decay as you go down. Now in the ocean, that happens. The current does decay as you go down away from the surface. The sheet is the wind. But in the northern hemisphere, the current goes to the right of the wind. In the southern hemisphere, to the left. So you're looking downwind. If the wind is from me towards you, the current will go in this direction. So that's the first change that takes place. There's a balance between the wind stress and the Coriolis force. The second thing that happens is the response to a pressure difference. So we play the same game again. We have water filling the hall. I put a partition through the middle, and I have more water on this side, my right, less water on my left. If I remove the partition, in a normal case, the water would flow from high pressure to low pressure. That's what happens even in the ocean. But the moment the flow starts, the Coriolis acceleration comes into play, it deflects the vector. And when the steady state is achieved, you have the pressure gradient force acting this way, the Coriolis force acting the other way, and the current goes this way. So it flows normal to the pressure gradient. So in this case, you have high pressure on this side, low pressure on this side, and the current goes into the wall. So this has implications. Suppose I have a coast. So I have a coast here. Okay, I have a coast and I blow a wind along the coast. I'm blowing it along this side, from me towards you. The water will be pushed away from the coast to the right in the northern hemisphere, and once it's pushed away from the coast to conserve mass, water has to well up from below, that's called upwelling, and the sea level has to drop. So a pressure difference is set up. There is higher pressure away from the coast, low pressure at the coast, and a current is set up along the coast. If the wind reverses direction, it's towards me, water is pushed towards the coast, the isotherms go down, sea level rises at the coast, again you have a pressure difference, but now the current is towards me. So this is something that you are not going to find in normal laboratory conditions. What this means is that if I have a wind blowing along the coast, I'm going to set up strong currents that go along the coast. In contrast, if I have a strong wind that blows into a coast, it merely redistributes the water along the coast. It doesn't set up those sea level gradients, and therefore it doesn't drive strong currents. It's still important for mixing, but it doesn't set up strong currents. So the direction of the wind matters with respect to the coast. And the direction of the coast is determined by geography, which is given to us. So what have we seen so far? We have these gyres in these 5 ocean basins. It's different from classical fluid flows, so that's one take-home message. It's a thin fluid, there's sphericity and rotation, and you have these subtropical gyres. It's subtropical because the average latitude would be in the subtropics. It's beyond the Tropic of Cancer or the Tropic of Capricorn. This explanation for this came in just 5 years following World War II. There are 3 papers, remarkable development. And I don't want to go into details, but it's basically conservation of angular momentum. You're putting some spin in by the wind. You have the westerlies towards the pole, and you have the easterly trades. They set up a spin, and to conserve that, you get this circulation. And because you have this Coriolis force, the boundary current goes to the west, the western boundary of each of these ocean basins. So you have the Gulf Stream on the east coast of a continent, the Kuroshio on the east coast of a continent, and so on. But these were all steady state theories, because the westerlies don't change direction, these trade winds don't change direction. So the steady state theories could be applied to these 5 ocean basins. The North Indian Ocean is different. And that was the inspiration for the International Indian Ocean Expedition, a remarkable event that took place during the 1960s when the Cold War was at its peak. It was a collaboration across many countries, and my institute was set up following the IIOE. So there is a lot that happened in India because of the International Indian Ocean Expedition. So what happens here is the wind reverses. You have the northeasterlies, the winds blowing from the northeast in January, and the southwesterlies in July. And you have a reversing current. The western boundary current that will be off Somalia here is equatorward in January, towards the equator, and it flows poleward, that is away from the equator, in July. So the current reverses, and this is what everybody wanted to see, what is actually happening. So there were several ships pulled in by different countries, and an international team that made the observations. Now, I need some focus for what I'm going to talk about. So I'm going to focus on just the coasts of India, the east and west coasts of India. I will use just a couple of examples to drive home some key points, and then look at how we go about understanding what we see in the North Indian Ocean. There was a lot that happened after the International Indian Ocean Expedition in the 1960s. But systematic hydrographic observations in the Indian exclusive economic zone, that is off the Indian mainland, I'm not talking of the Andamans, were made between 1987 and 1994. A remarkable set of 8 cruises, each lasting about a month to 35 to 40 days. And they mapped the circulation of the coast in a manner that allowed the development of theories. Earlier efforts were more scattered. So this was very clear and very focused. But note that there were just 8 cruises in 3 seasons, spanning something like 7 to 8 years. So each cruise takes about 30 days to go from, say, Kanyakumari to Okha, but we consider that to be taking place at the same time. We not only assume that, we assume that that is representative of that season in every year. So there's a lot that is averaged out over here. But that is how classical oceanography was done. And that is how the chart that Pai saw was put together. So what happens with the West India coastal current? Now this is the reversing wind, but that's a vector. I want to know what is happening to the longshore wind, because I want to know what is the wind along the coast. That is the one that's important to me. If you decompose these 2 vectors, you find that the longshore component is in the same direction throughout the year. So the longshore wind of the west coast of India is towards the equator in both winter and summer, but the current reverses direction. In summer, it flows the way you would expect it to with the wind, as I explained earlier, but in winter, it flows into the wind. So this is something we would like to explain. Why does the West India coastal current flow into the wind during the winter monsoon? The East India coastal current also reverses seasonally. This is the picture from March. This is the wind from March, and this is the wind from July. The current is actually stronger in March when the wind is weak, And when the wind picks up, and it is almost entirely along shore, an accident of geography, you have southwesterlies, and that is the orientation of the coast. So almost the entire wind vector is going into the longshore component. So it can drive a very strong current, but the current weakens. So why does this happen? Now it may seem that these are questions of academic interest, but there are practical implications. You can show that the fisheries of the west coast of India are determined by the circulation. The circulation determines why sardines dominate of Kerala and the Bombay duck dominates of Gujarat. We have actually shown that. Of the east coast of India, I have a different story. In the mid-90s, when I had just gone to NIO and we were doing this kind of work, that's when India started drilling of what's today well known, the KG Basin. And KG Basin, the drilling is at a very deep depth. It's about 1,000 meters. It was 10 meters at Ankleshwar, about 100 meters at Bombay High, and 1,000 meters at, in the KG Basin. Now, if you have ever drilled a hole in a wall with that mechanical drill, you know that you need to keep your hand steady. If it shakes, it's gone. You have to start all over again. So the company that was doing the drilling, I think it was BP, doing it for ONGC and Reliance, it picked March, April as the time to do the drilling, the first studies, because that's the time when the winds are weak, so they expected it to be relatively steady. See, now you have a 1,000-meter long pipe, and at the end of that is your drill bit. So you are standing a kilometer away from the point where you want to drill a hole and your hand is shaking. It's something you want to avoid. They found that the wind was indeed weak as expected, but the current was strong. They managed it. The oil companies are really good. After all, they drill in the North Sea and the Gulf of Mexico where you have so many hurricanes. So they managed it, but they had a question. Should they have anticipated it? The answer is yes. We could have told them the current is strong, and they would have had to face the problem, but they would have probably saved some time, and time is money. So the North Indian Ocean is different. Geophysical fluid flows are different. And how do we go about studying it? What we have done in the last several decades is to use what's called linear theory. As to what is linear and what is not linear, we'll come to a little later. But for the time being, it's enough to just follow it as we go along. So I'll ask just two questions. Why does the West India coastal current flow into the wind during the winter monsoon? And why is the East India coastal current stronger during March, April when the winds are weak? The basic theory is contained in just two papers, that's Matsuno and Lytle, and Dennis Moore's thesis, unpublished thesis of 1968. That's about half a century ago. And that's all you need to put together the explanation. And all this was linear theory. So what happens is the following. This is a solution from Julian McCreary's PhD thesis of 1977. So what's shown here is a rectangular ocean basin. You have a rectangular ocean basin, and you have winds only over this small patch. Oh, it won't come. Okay, this is the small patch over here. So you have winds only in the western part of the basin over a small patch. These are east-west winds blowing along the equator. This is the equator. And these are steady winds. They're switched on and then kept steady after that. So what is the response? The response is not limited to where that wind blows. After 35 days, this is sea level, you can see a wave going eastward along the equator, and it's almost reached the eastern boundary. This would be Peru if this is the Pacific, and this side would be Papua New Guinea. There's another wave that goes westward, it goes slower. So this is after 35 days. After 69 days, this wave has hit this coast, and there is an east-west current associated with that, which has to be cancelled at the boundary. You can't have flow into a continent. That was what Dennis Moore showed in his thesis, how to do this reflection. Now when this wave reflects, you have energy going poleward all the way to Alaska and all the way to the southern tip of South America, to Cape Horn. And it reflects back along the equator. In the meantime, this wave hits the eastern boundary, western boundary, and it reflects back. So this wave propagates all the way to Alaska. This entire process is over in about 3 months. about over a distance of about 10,000 kilometers, 10, 15, 20,000 kilometers, just a few months. So you have some wind that was blowing in the Western Pacific, somewhere off Papua New Guinea, and you are seeing its response at Alaska and the southern tip of Chile a few months later. It doesn't stop there. You see this wave, it peels back from the western boundary, and you look at its profile. It's fast near the equator. It's about 60 centimeters per second at the equator. If you go to the latitude of Cochin, that's 10 north, it's around 10 centimeters per second. If you go to the latitude of Los Angeles, which is around 30 north, you're talking of 1 centimeter per second. So at 1 centimeter per second, it goes all the way across the Pacific. And that can be tracked if you have a good enough satellite with an altimeter. That was available to Jacobs et al., who wrote a paper in Nature in 93, showing that the effect of the 1982 El Nino, similar thing, there was a disturbance in the Western Pacific. It was over in a few months all the way to Alaska and Chile, and then this Rossby wave starts propagating slowly westward. It slow vaults across the Pacific. In 1992, off Japan, in the Kuroshio extension, you could track that impact. It was the strongest El Nino of the century until 97. The signal was big, and you had an instrument that was capable of tracking it. So this is the other thing to keep in mind. There are two take-home messages here. One is the long memory. We are talking of decade, and this is at the surface. If you go into the deeper ocean, it is centuries. The ocean remembers. And the other thing is, you have a disturbance in one location, it can have an impact at some later time, maybe a decade later, at some completely different location. This is called remote forcing. There is no forcing of the Kuroshio. You are actually seeing sea level changes that are occurring, and you can track that because your instrument is sensitive enough to track that strong sea level disturbance created by the 82 El Nino. So why does the West India coastal current flow into the wind during winter? There are two simulations here shown for January and July. On the left is what's called a nonlinear simulation. That's with the full set of equations. And you can see that the flow into the wind in January is produced. It's not something that I can play with. It's a good simulation, but I can't break it into pieces and carry out the kind of analysis that I would like to. That can be done if the linear system can produce the same response, and it does. There are some differences between the linear, the right side and the left side, but in general, the linear system does produce what the nonlinear one does. As to what exactly is the difference between these two, we'll take a look at in module 3. But for now, the linear system does produce that current into the wind during January. So now I can play a game. What I do here is use only west coast winds. So from Karachi to the southeastern end of Sri Lanka, that's the left panel, only west coast winds. And on the right, from the southeastern tip of Sri Lanka to Chittagong, only east coast winds. So if you look at the current into the wind here, it's driven more from the east coast of India. So what's happening is that you have stronger winds off the west coast of India, but that's almost perpendicular to the coast. So it's just redistributing mass along the coast. It's not able to drive a strong current. It does drive a weak current in the right direction, but it's not quite what you see. On the other hand, the weaker wind in the bay, just because it is aligned to the coast, the entire vector is now going into the longshore component, it drives a strong current. It doesn't stop there. It has almost no impact over the rest of the Bay of Bengal because there is no wave that can take information eastward across the basin. It can only go westward, as you see here. So the wave that is set up along the east coast of India, it turns around here, the tip of Sri Lanka, and goes poleward along the west coast of India. And as it does that, it radiates offshore. And once it does that, it sets up the circulation. So what you see in red is high sea level, what you see in blue is low sea level. And there is a very close connection between the sea level and the current. That is what we saw. I mean, this is not a steady system, unlike what we looked at in that picture earlier, but it is not a very big deviation from the steady state. That is the strong impact the Coriolis acceleration has on the seasonal cycle. So the West India coastal current flowing into the wind is being driven from the east coast of India. So why does the East India coastal current, why is it stronger during March, April? You have waves being triggered out here, and they propagate westward. When they reflect off the east coast of India, they produce this strong current. In contrast, in July, if you look at the response only to east coast winds, it is a strong current and it is in the right direction. It is overcome by the other processes. So there are multiple processes that are playing off here, one against the other. The advantage of the linear system is that I can look at each in isolation. I can look at 1, 2, 3, 4, and so on, then add them all up. It's the principle of superposition that we used in school physics, and you get the result. So the winds are strong in March, April because of remote forcing. Forcing somewhere else, impinging on the coast, and causing a strong current over there. But it has implications for the drilling of oil that you're doing out there. Now this is a picture from the altimeter. It gives you the topography of the sea surface. Red is high sea level and blues are low sea level. In atmospheric science, in meteorology, you are used to drawing maps. If you look at any weather forecast, you will see maps of geopotential height and so on. For the oceanographer, none of this was possible. You were looking at cruises taking place over several months to draw those pictures. With the altimeter, it changed. Now there's a repeat cycle of 7 to 10 days, and every 7 to 10 days you get a snapshot. For us, this is the equivalent of what meteorologists do every few hours. But this is a remarkable development. This high in sea level that you see here in January and its low counterpart here in July, this moves incessantly westward over time. And what is striking about what you see of Kerala is that even if you were to use a transparency sheet, A4 size, of the entire global ocean, this stands out as one of the most striking seasonal features, what happens off Kerala. So for us, this was a remarkable development. It's not possible to study the Indian Ocean without this technology. I won't go into the details here, but you have a coastal waveguide, you have an equatorial waveguide, you have energy leaking from one to the other, you have these waves bouncing back and forth over the basin. What they do is to merge the entire basin into a single dynamical entity. So even if I want to simulate the current of Goa, and in shallow depths, as shallow as 10 to 20 meters, and at periods as short as 10 to 20 days, I end up having to simulate the entire basin. This is the effect of remote forcing. So I can't do an EIA study with just a small basin. It is tempting to do that, you save on computational resources. But if you are looking at anything other than the tides, you need to simulate the entire basin. That was linear theory. If the world were linear, I would have stopped there. And unfortunately, it's not. So what is nonlinear? Let's look at some examples. What you see here is the coast of Oman, and this is during the summer monsoon. You have southwesterly winds, so there's a wind blowing parallel to the coast. What do you expect? The water would move offshore, smooth Ekman flow offshore, and if that were to happen, this chlorophyll that you are sensing from satellite should just show you a red patch gradually moving away from the coast, more red near the coast and diluting as you go away. That's not what you see. What you see is the chlorophyll is concentrated in jets and squirts, and that seems to happen everywhere where you have these capes. This one has a particular name, it's called the Ras Al Haj jet. If you use a model with high enough resolution, this is about 5 kilometers, and this is current, not chlorophyll, you can produce this kind of signature. Now, this is not linear dynamics. There's no way you can get this from linear theory. In linear theory, you get that classical offshore flow and the classical coastal current going downwind. That's not what you see here. So how do we go about solving these equations? This is a typical thing that we do. So in a model, what you do is break the ocean into stacks of boxes in the horizontal and in the vertical, In the vertical, you have thinner boxes near the surface, and the thickness increases as you go down. It could be 1 to 5 meters or 10 meters near the surface, and as you go down, it would be a few hundred meters. The last box that you have, last stack would be a few hundred meters. That's to save computational time. The language used to solve these equations is still a variant of Fortran. Probably never going to change because these codes are a million lines long, and it's easier to keep Fortran going than to change all these codes. So what is a linear system and what is a nonlinear system? So suppose the system I'm studying, let's say the North Indian Ocean, is this box. We don't bother about what it is. It could be anything. It could be mussels, it could be North Indian Ocean, it could be just about any stuff. So it's a linear system. I have an input I and I get an output O. So the system is what you have on the left hand side is a differential equation, the homogeneous part, and on the right hand side is the forcing. So that is I. In this case, I is the wind, in our case. So in a linear system, if I have I1, I get O1. If I have I2, I get O2. And if I put I1 plus O1 as the input, I will get O1 plus O2. So I can, output is proportional to input. The whole is the sum of the parts, and I can break the forcing into pieces. That is the game I played earlier. In a nonlinear system, I1 plus I2 will not give you O1 plus O2. Simply put, that is the basic difference. It could be more, it could be less. It depends on the system and it depends on the circumstances. So output is not proportional to the input. The whole is not equal to the sum of the parts. So you cannot play that game. You cannot break the forcing into pieces. So what really is the problem here? It was about a century after Newton, Principia Mathematica, which laid down the laws of motion, that Euler wrote down the equations of fluid flow. This is basically what he had put down. So what happens is the following. Suppose in this room, you have many thermistors measuring temperature. And let's say the temperature measured by each thermistor does not change in time. So you have, say, 50 thermistors at different locations, and each thermistor is showing you a steady temperature. But there is a flow, and there is a gradient. You have an air conditioning on one side and no air conditioning on this side. So it's going to be cooler there and it's going to be warmer here. So suppose there is a flow of air from that end to this end. A parcel of air, if I were to track it by some means, will have a temperature T1 which is cooler over there, and by the time it comes here, it will have a temperature T2 that is higher. The temperature T1 there has not changed. The temperature T2 here has not changed. So why has the parcel's temperature changed? Because it has moved. This doesn't happen in solid body dynamics. You're just tracking it in space. So what happens here is the following. There is a change that comes because of the motion. Here it is U. S is any property, and you have a gradient. So you have U multiplying that property. This is nonlinearity. So when we play this linear game in brute force terms, I would just drop these terms. To the extent that can be done, your linear theory is valid. To the extent it cannot be done, and it's not valid in those boundary currents, western boundary currents, you have a problem. This nonlinearity is fundamental to all fluid flows. It is also a fundamental property of what are called complex systems. They have certain properties, these complex systems. One is self-organization into patterns. One example is clouds. If you look at a satellite picture, you rarely see isolated clouds. You will see bands, or you will see a cyclonic kind of circulation or anticyclonic kind of circulation. So they are organized. So this self-organization into patterns is a property of all these complex systems. There is what is called chaotic behavior. There is chaos. In simple terms, if you change the conditions, initial conditions slightly, there is divergence away from that. So if you have two initial conditions which are separated by a small amount, as you continue forward with your model in time, that difference is not going to remain as small as it was in the beginning. It's going to amplify. This is chaos. So you can't make a prediction beyond some time. It won't be of any sense. Atmospheric weather forecasts, for example, are never made beyond 7 days. And every day they update it. Another property is what's called fat-tailed behavior. you expect a normal or skewed normal kind of behavior with the extremes being small. But that's not true in complex systems. You get many more extreme events than you would expect from linear theory. There's also what's called emergent behavior. We'll take a look at what this is, but it's a result of nonlinear interactions. Now, complex physical systems are studied using what are called partial differential equations. It's a very well established body of mathematics, and you can use that to study, for example, climate. But there are complex systems that are not amenable to these partial differential equations. They are called adaptive systems. This happens in biology and in social dynamics. In simple terms, once bitten, twice shy, which is adaptation, cannot happen for a Rossby wave. That thing will just keep propagating westward the way it did, no matter what you put in its way. It doesn't understand that. It's not once bitten, twice shy. It behaves the same way no matter what happens. But that's not true of, for example, investing in the stock market. You make money, you're drawn to it, you lose money, you may go out. So that's a problem with biology. Using partial differential equations is something that's not easy. This is Lorenz's classic attractor. The equations, don't bother about the details, they're very simple equations, they're not very complicated. But they produce this kind of pattern with two lobes. The solution is bounded, it doesn't go to infinity. But you could spin between maybe an ice age and a warm state. And where you will be is determined by these coefficients, constants. You change the constant beyond some threshold and you could just spin off into a completely different climate. I'll give you a practical example of chaos. My colleague dropped 3 drifters. These are buoys that float in the water. On 29 November 2016, this is the coast of Gujarat. They went together for about a week and then they diverged. A few months later, they were all over the Arabian Sea. Now this has practical applications. On 8th of March, it will be 10 years since MH370 went down. It's still unclear what happened. There's no closure for the people who were directly affected by it. When it went down, and what was available then was data from the engine. Only that was available. The black box, nothing. The pilot had probably switched off the communication system. There was nothing coming from the cockpit. So the engine sensor could be tracked, and this is the arc on which it had last been seen. This green box is roughly where it's imagined that it probably went down. It's a vast area. Now these are drifter trajectories. They follow what is called the south equatorial current. That's linear theory. And 8th March 2014 is when MH370 disappeared. Sometime in March, April 2015, one wing piece was found of Reunion Island on the other side of the Indian Ocean. It had taken a year to cross the basin. Now, this is the south equatorial current, but look at the scatter. That is chaos. And that's why I told my family there's no way they're going to find it. It was a terrible job to go out on your shift day after day, knowing fully well that you stand no chance of success. A terrible job. It went on for over a year, but those hydrographers had no choice. They had to do it to show that they were doing something. 10 years have passed, we still do not know what went wrong. And that's because of chaos. Now you have these propagating waves. So you would expect that if you have high variability here, this Rossby wave would carry that information all the way across, and you will have high variability over time throughout the equator. That's not what happens. This is a map of variability at a period band of around 3 years. Blue is low variability and red is high variability. So there are regions where nothing seems to happen. The central equatorial Indian Ocean, the west coast of India, coast of Oman in patches, the Gulf of Aden. The question is, why does this happen when this wave goes all the way through? Why does this high variability not show up all the way across? If you take a linear model, you can simulate that, but it's very smooth. You look at the coast of Oman. It's a very smooth solution, unlike what you see here. This is a nonlinear simulation. It's more accurate, but I can't understand what's happening here. In the linear simulation, two processes cancel out where you get those minima. This is emergence. These are properties that arise because of nonlinearity. Done? Okay. So this is insight, this is simulation, and when you simulate, the only way accuracies are good is if you assimilate data over time, which is done in a forecasting system. You can't do that when you're simulating climate, and this is the problem. This is why understanding is still important. This is the deviation that you see in models in IPCC. I'll skip this. So you have complex systems, you have big data and models, and there have been two competing views over several centuries. This is what Professor Rodam Narasimha showed. And this competition is serious now because of what is called big data and artificial intelligence. Does differential equations still matter? The problem is that you need insight, because you need to understand why these models are going wrong when they do so. Why is there such a big divergence between climate models? Because serious decisions are made based on that. The other problem is we think that we have a big data problem because satellites give you a huge amount of data day after day. But in earth science, basically you are solving a sparse data problem. There are parts of the matrix that are dense, very dense, because you have a lot of information from satellites. The rest of it is practically empty or very sparsely populated. So to sum up, remote forcing, long memory, linear wave theory, but it's a complex system. This is my last bit. You have sufficient linearity to be exploited. The blue regions are where linear dynamics dominates. So that's like a full toss. To throw it away would be foolish. Thank you.
Thank you. Thank you very much. We have time for a few questions. And the first one, in fact, is about the slide just before this. This is a question from Meenakshi Sundaram Murali. Please, no, you don't need the slide for it. Please comment about any renewed scope now for data science professionals in India, especially for applying machine learning, AI, and for studying the oceans.
That's being done. But what happens, in my view, is the following. You have huge amounts of data coming from two sources. One is satellites, and the other is high-resolution models. So that is where you will end up applying your AI. To me, it's like looking, satellite sees only the surface. It can't see below. It can't see anything below. So what you are doing is you're going to apply AI to a small subset of a large problem. It's like looking where you have light, not trying to find where actually you lost the thing. You have a lot of light in some place, most of it is dark.
Okay. There's another question from, where is it? From A. Bhupalan. How do you study the impact of earthquakes under the Indian Ocean using which models?
That's completely different. It's done using seismographs. So there are instruments located everywhere around the world, and they can track the quakes irrespective of whether it occurs at the bottom of the ocean or is terrestrial. It doesn't matter. But if you want to look at what happened near the ocean bottom, then you need ocean bottom seismometers. They are much more expensive to deploy and maintain. So there's not too many of them.
We'll take one last question now. There are some more questions which maybe we can come to later. Dr. N. Parthasarthi asks, can the composition of air influence the wind current, especially the carbon dioxide content? And do the wind currents influence the ocean current, or is it more due to temperature?
I didn't get that.
So the first part maybe, can the composition of air influence the wind current?
No, it doesn't matter. It's just that if the carbon dioxide increases, the winds may change because of strong storms and so on. Then it has an impact. But the chemistry itself does not matter. It doesn't change the applied force.
Okay. Yeah, thank you. There are more questions, but maybe we will come to them at the end of the session. Join me in thanking Dr. Shankar again.